So I'm from Verified Systems. We are part of the project partners of HubCap. So we're one of the SMEs. And when Hugo sort of explained the big picture here, I'm showing more the perspective of an actual SME using HubCap and providing services and features to the platform. So this is work that has been done with Jörg Brauer and Oliver Möller. And I will explain a bit more what this work entails. So we are interested in model-based testing, but also to combine model-based testing with co-simulations. So here's a short overview of our talk. So first, I will say a bit more about RT Tester and RTT MBT, and explain how the form of model-based testing that we are doing in our company can be recast in the context of FMI co-simulations. So FMI is kind of this common denominator of HubCap. So to exchange, for instance, models, we can use the FMI2 standard and the formats of FMUs so that different tools can talk to each other. So that is the means for, or one of the means we have for exchanging models. We have an experiment within this platform that users can try. So the aim is really to show users how you do model-based testing with our tools, to have some way to modify, to experiment, to change the model, to change the code. So this is also facilitated by our experiment. And I will give a bit of an update. Hugo has already nicely shown the sandbox and the potentials of the sandbox. And I will explain also what we currently manage to provide within the sandbox and what the work in progress is there. And this will also involve a short demo. And lastly, a bit of conclusions and future outlook on where we go from here and what are the next steps going to be. So, RT Tester in a nutshell. So RT Tester is the showcase tool for Verified Systems, our company in Bremen. It provides a bespoke language, so it's a specialized language for software testing, which effectively is an extension of the C language. We call this RTTL, so the RT Tester language. It has additional features so that we can easily formulate test assertions which are evaluated. We facilitate the stimulation. So stimulation is providing inputs to the system that we are testing. And there's all sorts of features that are useful that we can use, for instance, in terms of expressing timed stimulations, delays, waiting for signals, waiting for signal changes. So all of this, what the tester really wants when he writes his tests, is provided by this language. And it's centered around the notion of abstract machines, which are sort of concurrent, independent entities that can fulfill certain jobs within the test, either checking the reactions of our system to test or providing the stimulations, the inputs. And as I said, there's a plethora of constructs that the test engineers and programmers can use. And there's also logging and tracing facilities so that after you run your test, you have proper ways to see if your test has executed the way you expect, that you have also some evidence for the testing and some traceability. And what's important is we support different levels of testing, from unit tests to integration tests and system tests, combined with hard and software. And last, we also have a model-based testing plugin for our tools, or an extension of our tools that facilitates model-based testing. And all of these tools are qualified according to DO 178B RTCA. So these tools have been used in industrial projects with large partners such as Airbus. So in terms of model-based testing, I just want to give you a very quick idea of how model-based testing works with RT testers. So we have a model which is expressed in UML SysML diagrams, and essentially these are state machines, hierarchical state machines, and these models really describe what the system does that we are testing. So we are describing the system under test. And based on the description of that system, we can compute, on the one hand, how we're going to stimulate, what sort of inputs we need to provide to the system to perform certain kinds of tests, to achieve certain test goals. For instance, we want to reach certain states, or we want to have certain coverage of the system. And what is also very useful is that we can automatically check if the actual system that we're testing exhibits exactly the behaviors that we specify in our UML SysML model. So this model has this dual purpose of allowing us to generate test procedures automatically, and also to check when we test that actually the behaviors that we are seeing from the system under test are actually the ones we would expect according to a model. So these SysML diagrams are, as I said, implemented written in terms of hierarchical state machines. We capture high-level requirements in this system that we can extract from specifications, and also abstract away from all the low-level details of the hardware. And I will later say a bit more how co-simulation FMI also facilitates that. So to make this all possible, our RTT-MBT tool uses cutting-edge techniques based on SMT solving to extract those timed stimulations that we need to achieve the test goals, and also some features then to validate that our requirements coverage is achieved. And we can even produce systems under test as a mock-up, completely based on the model. So we can also provide such systems to see this is how the system would look if we just use the model as a basis. So it's a very quick example. So this is very simple. Our actual systems that we use with our industrial clients, they are much more complex than that. But this kind of shows you a little bit how we can capture testing behavior. So we have an indicator of a car which is flashing. It is initially on, and we have a timer here, which when it elects this, we have a transition from the state on to state off, and here the lamps are both set to 0. And then again, we reset the timer here at this point, and we wait until the timer elapses, and when it then elapses, we're setting the lamps to this state, L old, which was the initial state. So this guarantees that maybe one or both lamps are flashing depending on the mode. And these transitions we see here in states are mapped to requirements. So when we execute our test, our tools can actually see, are these transitions taken? And if they're taken, then we know that we exercised, that we tested these requirements, and this can go into the coverage analysis. And this model, this is of course just part of the model. The actual model is more complex. It also deals with emergency flashing. So this could be a machine, which is a state machine, which is deeper inside the system. And the actual system can do other behaviors, can incorporate other logic to drive the system. So how is all of this related to FMI and hubcap? So first, just a quick recap on FMI. We've already heard a bit about what FMI is. So just the things which are relevant is that FMI facilitates co-simulation. So we can have different independent simulation components within our FMI setup. And these are all managed by a master algorithm. So these FMUs could be individual simulators, and they are controlled through an API. It's a programming interface. It's a set of functions essentially that are called from a master algorithm. So the master algorithm is kind of the big overload that kind of orchestrates all these FMUs. And this is already provided by the Into CPS project and application, in particular the COE, the core simulation engine. And these FMUs are then provided by the hubcap, for instance, by the hubcap components and tools. And in our case, we also provide these FMUs as outputs of our tools. So this is where actually the magic happens of the executions of our tests. And these components, as I said, are isolated from each other. They don't communicate with each other directly, but only through the master algorithm. And this is very important because timing is a very important thing to consider in testing. So we have to make sure that when we execute our model-based tests, or actually tests in general, that we execute these tests at the right granularity of timing, that we are not kind of missing things that we should actually see within our observers and checkers that check the actual behaviors of the tests. So we don't have to worry about the master algorithm, but we do have to worry about the FMUs that we are producing. So how do we combine model-based testing in the form that I've explained it with FMI? So what we've done as part of HubCap so far is to recast our model-based testing framework and tools to work in the context of FMI, or the FMI standard 2.0. So what we do at the moment is that we execute the system to be tested as an FMU. So this could be a real system that we compile from code. It could be a mock-up system. It could be something. At the moment, we have a simulation that we wrote by hand for this demo project that we're using. And this can be compiled down to an FMU and execute separately. We also execute the test procedure as an FMU, and this test procedure contains two parts: a stimulator, which has outputs that feeds our system under test, and checkers, which then run as independent abstract machines as part of our RT-tester tool framework. And these checkers are really just sitting there and looking, what is the system doing? Is it doing the things I expect? So these checkers see also what the stimulator does. So for instance, I'm setting now my turn indicator lever, and now I need to see something happens. I need to see that these lights are starting to blink with a certain frequencies. So these checkers then tell us at the end of the tests if everything failed or something, everything worked or something failed. We never expect everything to fail, but usually testing is also successful if things fail. So that is the point of testing. You want to see if things, if there are problems with your system. And lastly, we can also have FMUs as observers. And there's also a collaboration possibility in terms of HubCap here, that we can work with other tools like the Into CPS applications that provide already such features. But this is something I will say a bit more at the end of the talk. So here's a few implications that we had to consider when we did this kind of adaptation. That real time, usually we're dealing with real time when we do tests, kind of wall clock time, sometimes even distributed around different network clusters and real hardware. But this real time now becomes simulated time. So we can perform, of course, in FMI simulations within an instant of a time that in real time would maybe run for an hour. So this is very important, that this, our tests, the notion of time is adjusted at all points. So we actually do need to measure time, and the behavior of our system depends on it. Then, of course, the parameters, as I said, need to be carefully chosen. So we need to make sure that our time granularity is appropriate, but this is always a problem with FMI core simulation. So I wouldn't say this is particular to model-based testing, but it needs to be, of course, considered. And I think Jose had a question about hardware in the loop testing, and this is potentially possible with our tool because we can generate, as I said, FMUs for the system under test, and the FMI interface is really agnostic to what is running underneath. So what is important, that we build this connection between the real system and the FMI interface. But if we can build this and our simulation can run fast enough, and as I said, RT-tester has been built for real time, then this is certainly possible and provides an interesting possibility to use the FMI standard as a kind of unified way for system under tests to talk to the actual model in a way. And of course, our FMUs, and this is something we recently looked at, need to be able to run outside the context of RT-Tester, the RT-Tester toolset, which is a kind of new scenario for us, because before we always assumed that we can run our tools inside the RT-Tester toolset, and this is changed now. So I'm going to the next slide. So in terms of hubcap, what we have done so far is to integrating our tools into this hubcap platform. So we have RT-Tester, a full version of RT-Tester running with FMI support. So the user can use all the features of RT-Tester, this RT-Tester language. So it can also change the low-level stimulation code, which is usually generated from the model. So it gives sort of this additional features for that. So this version, of course, is tied to the hubcap platform. We have our model-based testing extension, which run as a limited trial version. So they can only be run with the demo project. But in the context of this project, also the user can try all the features of the RTT-MBT tool extension. And we have a GUI, which is already freely available, is Eclipse-based. So all of this is driven by Eclipse plugin for GUI. And to illustrate model-based testing, we have this turn indicator demo that I've kind of shown a little bit before, where we have an indicator lever that can either be operated left or right. We have emergency flashing behavior in this. It's not a very complicated model, but it's just having the right level of complexity that we can do some interesting testing with it, and we can see what happens if we execute this test and change the parameters. And also we added, as I said, a system under test and observer FMUs so that the user can see something. And the use cases for this hubcap experiment from our side are to be able to modify test generation parameters, to change the stimulation scripts directly, inject faults. That's currently not implemented, but we will have also faulty system under tests, and to look at things like the test results and the coverage analysis to see if the test goals have been achieved. So a few challenges we had with this virtualization technique is partly due to license handling, but I think this is kind of a common issue with the platform, that we have to provide, depending on the license agreements, additional features for tools to be able to manage that. And as I already explained, we have to be careful with time, replacing the simulated time by real time. And an interesting part of this was to consolidate the model interface. So a SysML model will provide its own interface with the FMI interface. So there's a little bit of, let's say, design that needs to be there. How can these two interfaces work together? And at the moment, this works completely automatic. So the model interface is mapped onto an FMI interface. But in the future, we might think of different ways here that also gives more possibilities to align these two interfaces so that the model can remain at a level of abstraction that is appropriate for it, where the FMI interface can be maybe more geared towards a system. So if you want to use foreign FMUs, then this would be interesting. And then also the communication with the COE, that's also a part. We had some kind of minor stability issues, but this is something maybe that can all be done nicely. So in terms of the GUI, we have a few actions there, which the user can perform specifically for the FMI work. And I will not say too much because I want to show this in a demo. So here we have our RTT-MBT GUI running inside the Sandbox. And rather than talking about this screenshot, I actually try to show you a small demo how this actually works. So I hope you can see our GUI. So we can here, we have our Eclipse workspace, and I can import a project first. So based on a model, so here I have a model which I've already generated and exported as an XMI file. I can now import this model. So we can also show this model. I'm skipping that now, but with the Papyrus extension, we can have a look at this model as well. Based on this model, I can generate first an FMI adapter, which I need in order to export my test procedures as FMUs. And I can now generate a test procedure. So in my test generation folder, I have various test procedures, which are specified in different ways. And this test procedure has some configuration, and I'm now going to generate this test procedure, the code for this test procedure. And we could then even inspect the code. So this is actually the code that's been generated. It's not quite C. It's kind of C extended a little bit with our RTTL language. But you can already see that there's some stimulations here where we set the turn indicator lever to 1. And after I generated this procedure, I can then compile it down to an executable. So I'm doing this now. So I'll compile the test procedure. And now I'm going to generate an FMU from this test procedure. So I create an FMU archive. And this has worked so far. We can see the output. I can start the co-simulation engine. I've already done this, but the GUI also gives you this possibility. And now I'm hoping this works. Sometimes we have occasional hiccups, but I will have a look now what happens here. So you can see here there's different signals that our application provides. And if it works, we would actually see some signals here now. There is an issue here, maybe a hiccup. As I said, there's still some slide communication things that we need to look into. I will maybe stop this now and see if I can stop the COE and see if I can start it again and just see if I can do that. If this does not work, there's also a video available which we can make available, and you can have a look at this video, and that replays also what should happen. So I'm starting the COE again. I'm trying to run the test. Yes, and now you can see that actually our lamps are flashing. Here, the turn indicator lever has been turned on. And we can then have a real-time visualization of this test. And I can then, after I've run my test, also look at the test data. So if I refresh this, I see there's a little sign. Oh, it's not good. Well, from a testing perspective, it's good, but it means some tests failed. And this is exactly what we want as a tester. So we see here our test checked properties, and there's here an observed value, an expected value at a certain time in our test. But if we go further down, we see, oh, there's a test that failed right at the end. So here we're expecting a value of 1 for our indicator, and we got a value, we saw a value of 0. So this is kind of a thing that the user will be able to do. And lastly, we can also export our FMU. So if I click on the FMU, I can say here, I haven't integrated this yet in the GUI, but there's a possibility that we can run a script to export this FMU, and then we can use other hubcap tools, for instance, to use these FMUs or to visualize the test data. So there's quite a lot of possibilities also in terms of hubcap. So, oh, I did have my full screen. It was probably on another screen. So, to finish the talk, so we've done the demonstration. So I will give a few more conclusions in future work. We haven't so far executed our, oh, 1 second. I think I'm struggling with my keys here. Okay, I hope this is stable now. We haven't so far executed our FMUs with the Into CPS application. Oh, I think I leave this. I think this LibreOffice is all a bit unstable. I just use again this interface here. But what the next step for us would be to use the Into CPS application and see if we can run those FMUs with the Into CPS application and maybe profit from features of that application as well. This should be in principle now possible because, as I said, we've made these FMUs RT-tester independent. And also the next step that we are looking at the moment is to see what other possibilities there are for hubcap tools, let's say collaboration and possible interchange in terms of observers, visualizations. And we want to improve the GUI a bit further so that the steps that I showed you with FMU generation will be done automatically in the background, and we also see a bit more output from the COE and look a bit more at the stability of everything. And an important future work is to think about the linkage of MBT and FMI interfaces, because on the one hand, we might be given an FMU where we cannot change the interface. So in some way, we need to build a bridge between the two. And in terms of model-based testing with RT-Tester, we already doing this all the time, basically, because the systems we are testing, the interfaces are just there, but our models don't want to be expressed at such a low level of interface, but at a higher level where we maybe just say, here's going to be an alarm somewhere in the aircraft. But how we detect this is part of the interface then to implement. And this opens then possibilities for black box testing of foreign FMUs. So essentially, that's most of what I wanted to say. And if there's any questions, then I'll be very happy to answer them. Or Jörg, who is also in our chat.
Yes, so any questions for Frank and Jörg? Maybe I can ask a question to Jussi, who had the question earlier. Would this be of interest in the setting you have?
Peter, you're not asking me, no?
No, I'm asking Jussi.
Okay, Jose, yes.
May not be able to unmute himself.
Yes, sorry, I could unmute it now. With the modeling tool that we use in Oticon Medical, and I can already relate to some small state machines that we could try to verify in this way. But I don't know if this tool is it freely available. And now I'm thinking out loud, but I would imagine that the hubcap being a cloud environment, it will be difficult to communicate with our own offline tool. Maybe you can put a few words in that aspect.
Well, our tool will be available for trial together with this turn indicator project. But if there's further interest, then of course we have tools, commercial tools, and we will be very interested to talk about if you be interested in using those tools. So at the moment, the hubcap, we only support the demo project for the model-based testing facility.
Mm-hmm. And just one more question, maybe I wasn't fully clear. If we have our own tool that is executing locally in our PCs, for example, here in the company, can we communicate it through FMI with the tools that are running in a hubcap sandbox?
So at the moment, I mean, the sandbox you are seeing here is in demo. It's not yet released. We're just trying to show that you can actually do these things independently of what OS you're using and have it available in a browser like this. In the long run, we definitely want to be able to enable people to upload into their own sandbox any tool they would like to have and play it together with the other tools that they have installed for the sandbox. we're not there yet, but we will be getting there. Does that make sense?
Yeah,
Okay.
yeah, it does, definitely. I have a few more questions, but I think we can take them offline.
Okay.
For sure.
Just one comment from my side. I mean, you could export an FMU outside of the sandbox and then use it locally in your tool, together with your tool. That for sure should be possible in the future without problem.
Exactly. Yeah. That is the use case we're anticipating. So towards the later stages of the project, that we can actually take an FMU from somewhere, we can write a model for it, and then we can use our model to test that FMU. But that will be something that will come a bit later. We are still at an sort of early stages in terms of the potential of this.
Okay, given time, I suggest we move on to Nick's presentation. Nick, do you want me to share the PDF, or do you want to do it yourself?
Well, first of all, can you hear me?
Yeah, we can hear you.
Okay, that's good. And if I share my screen, can you see that?
Nothing yet.
Damn. Oh,
maybe you need to remove your sharing, Frank. Frank, you're still sharing, are you? Yeah. Try to do it again, Nick.
Share. Okay, just a sec. Share that one. And
now we see your screen.
Okay. Is that full screen?
That's full screen.